hydrogen mission where they want to implement hydrogen in various locations, and they want to have mandatorily green hydrogen in various sectors, especially the transportation and fertilizer industries and metal production. For example, steel company uses hydrogen quite a lot, and refineries, they use it to trap the sulfur, and in housing, powering the houses, and eventually aircraft and sea carriers. So essentially, the hydrogen is going to take up a significant fraction of our lives, like wherever we are looking into the energy. So there is a good reason why we have to spend time and investigate energy into the hydrogen business. And good thing is that the problem with hydrogen is that you cannot go with, like, say, I'm a physicist, I'm going to solve it. I'm a chemical engineer, I'm going to solve it. It's really difficult. So we need to have complementary expertise coming from multiple domains in order to solve this interdisciplinary challenge. How we are going to split water, how we are going to store the hydrogen, how we are going to transport hydrogen. So there is like a range of problem statements. And that's where we came up with this beautiful team. Myself, Aravind here, we work on materials and device physics. We are in this domain. And at the bottom, you could see that Professor Ranjit Kumar Nanda, he is our like a fantastic simulation person who does density functional theory and other quantum chemical calculations. And on the right side, you could see that we have a very young and brilliant person who works on systems level design, and he does modeling of all those things. And on the top, you could see Professor Kamlesh Hatwa. What he does is he works on electronics, and you could wonder why electronics person is here. Like, for example, you connect solar cells to electrolyzers. There is some electronics in the middle to match the load profile. It's a kind of, you need weird combination of people, and we have that weird combination of people to solve this big problem. And you could see that the top two, myself and Professor Kamlesh Hatwa, we are experimentalists, and Ranjit and Himanshu, both of them are simulation guys. And we have a person in the middle who tries to integrate both of us. And so Professor Raghunathan Rangaswamy, he has a great expertise on systems integration. So essentially, I think we are looking forward to really work as a team and solve this big challenge. So far, we have been working independently with minimal collaboration, and I think this center establishment from the Institute of Eminence grant is expected to contribute significantly to this hydrogen business. And when we framed our mission, we have been very careful. Like, typically, whenever we talk about any academic institutes, we say that these guys do fundamentals, they don't come to the reality. I think that is always there. Unless you go to institutes like Helmholtz Center Berlin, where Fatwa is working on, I think they're really like at the forerunners, connecting the academic research to the real world applications. And we did a kind of nice survey of similar institutes, and we kind of came out with two missions. One is immediate or urgent requirements, which will be very much industry centric, and futuristic ideas, which are exploratory. And with the immediate urgent requirements, what we will do is, like, within, like, we are targeting something like 2 to 3 years down the line, we will be able to successfully assist industries in trying to connect solar panels plus electrolyzers. We have well-established solar panels, we have well-established electrolyzers, and I think it's about integrating these two and try to see how they will meet Indian requirement. That is what essentially we're going to do on the left side. In the long run, I think we work on direct solar water splitting using photoelectrochemical systems. So we kind of deconvoluted the industry requirements as well as academic requirements, or immediate requirements, or exploratory or futuristic topics. And being said that, with the mission, I just want to show what we are capable of. I think that something is very important. I think talking is different and doing is different. And that's where I just want to highlight two important things. In the combination of people we have, we work all the way from like atoms to the significant like large scale systems. And I'm going to give you a few examples. In the solar water splitting, typically, like, we have nice silicon solar panels. Why can't we use that directly to split water to generate hydrogen and oxygen? That's a very common question. The thing is that silicon is not stable. You have to protect them. And thing is that when the whole world is struggling to find out nice material, our group discovered this specific class of halide perovskite to be very stable in almost all the extreme conditions, including strong acids and strong bases. And we have successfully demonstrated water splitting, like to generate hydrogen and oxygen with this specific material. So this paper, there's a bunch of papers from that one. One is from Angavante Shimi International Edition. The other one is ACS Applied Materials and Interfaces. And we also, in fact, we were working on something on water splitting, and we landed up in a very weird invention, like white light emitter. That was not a part of our business at all. We were like really working on something. We eventually ended up somewhere, like where we work on this structure. You could see this structure right here, which is like literally two chemicals where we tuned the atoms and we solved the crystal structures. What we essentially found out is that if we introduce distortion or a local asymmetry within the crystal, those materials can be very good for bright white light emission. In fact, this material we were like honestly targeting for water splitting. And on the way, a student came and then said, like, we find something interesting. Let's explore this. And that's how this invention came across. And in fact, we have patented this specific material and its technology. And this one won the DST SERBS Technology Translation Award. And this paper was also published in Communications Materials from Nature. And this is the material that I was talking about. I'll quickly go into like the kind of atomic level tuning that we have done. This is just a crystal structure of the material. For those who are not scientists, like our guys working in research, it might be difficult to understand. The green atoms are predominantly the halide atoms. The one in the middle are like metal atoms, and the large one in the middle is the A-side cation. In our system, what we have done is very simple. Instead of using only one side, like you see that there are two same colored atoms. Instead of that, we try to mix the two with the different bond lengths, and that essentially led to a distortion in the system. I don't go into the detail. I just want to give you a feel how we atomically tune the system, and that is achieved. Like, and then we have solved a very nice crystal structures. These are actual crystal structures. You see that when you have a two indium, this Ag has two equivalent bonds on two sides. Same thing is true for bismuth. However, when you try to put a mix of indium and then the bismuth, you see that Ag bond lengths are different. This is actual distortion. We solve the crystal structure. It's not some random nice image, but rather the actual crystal structure we have solved. And this system led to a significant increase in the excited state lifetime. People working in phoric catalysis know the importance of this lifetime. They always want to increase the lifetime significantly to microseconds and milliseconds. What we have found out is that when we introduce those distortion, the lifetime increases from somewhere from nanoseconds to more than microseconds. And we are planning to use these kind of materials in water splitting. And now I also want to show that this shows that how we really work at the atomic level. And here we work on some electrolyzers too. We work on large scale system where we convert carbon dioxide to products. Although it's not related to hydrogen, but I just want to give you a feel. We work all the way from atoms to the complete systems also. With that, I would like to bring in Professor Himanchi Goyal, who will talk about the simulation part. Himanshu, on to you, please.
Thanks, Arvind. Yeah. So Arvind nicely talked about his expertise in the science part of the problem. What I do is more engineering aspect of the problem. So once we discover some new novel material, which we are going to use for the hydrogen production, the question comes, how do we optimize the reactor at the lab scale first? And how do we then take it, scale it up to industrial scale? So my expertise is in the area of using high performance computing, data science, applied mathematics into chemical engineering applications related to clean energy or process intensification. So I have been working in these areas mentioned here, like multi-phase reactors, using electrochemical cells, combining them with machine learning to develop some really fast, efficient algorithms that can be used for design and optimization. Next, Arvind. Yeah. So in the past, I'm here showing just few examples of what we have achieved in the past few years. So here the picture showing biofuel production. These are some of the most advanced simulations developed and performed in the literature in the area of biofuel production. We're combining the molecular scale in the form of chemical kinetics with the actual multi-phase reactor scale simulation. So bringing basically transport as well as kinetic aspect together. We have also done under process intensification, we design different type of structured reactors using alternative energy sources like microwaves into chemical engineering applications. And then once we develop these state-of-the-art models, we combine them with data science techniques like artificial intelligence to reduce the computational cost so that we have really fast computational models and we can use them to optimize these lab scale systems and also use them for scaling them up. So we are really excited to be a part of this multidisciplinary team so that we can all work together, bringing physics, chemistry, and engineering skills to actually solve some real world problems. Thanks, Arvind.
Thanks, Himanshu. Now I'd like to pass the board on to Ranjit. Ranjit?
Hi, Arvind. Thank you very much. So thanks, Himanshu, for introducing his subject. So I entered to this center as a person who has expertise on understanding the quantum mechanical phenomena at the atomistic level. So my group carries out fast principle electronic structure calculations and develop models. So that's why I say that I provide a DFT plus approach to provide insights into this center, CPEC. So for example, as far as the battery concerned, my group has a very wonderful expertise. We involve density functional calculations. We induce ab initio molecular dynamics and nudge-elastic band methods to find out the electrochemical efficiency for battery material that include cathode, electrode, and electrolytes. For example, here I demonstrate how the graphene is a new 2D host material can be treated as a host cathode material for the aluminum ion batteries, and the predictions are based on all these three simulations. So Arvind, could you please go to next slide? Okay. So not only that, my group focus on the battery as the central demands, we also focus on the electrochemistry, be it electrocatalysis, photocatalysis. We examine the CO2 reduction. So that's a part of this. So this study will complement the part of our water splitting and CO2 reduction. We can develop reaction mechanisms eventually leading to the reductions from starting from the beginning to the final product. For example, I will demonstrate how CO2 ended up becoming methanol through several steps. And at each step, what is the potential barrier that one has to go across, and whether the product can be formed or not. And that's why the analysis can be made through free energy analysis, a thermodynamical analysis. Also, not only that, I focus on making the reaction mechanisms. We also create band gap engineering. As the left-hand side of the figure suggests, it's very crucial to know the band gap, because that works very well to tune the excitations. So my group pursue the model Hamiltonian approach and the DFT approach to see how the band gap can be engineered through chemical doping, defects, vacancy, and so on and so forth. So a detail can be found from the papers referred here. So I'm excited to be part of this center, contributing towards creating clean energy solutions. So we're looking forward to working on it. Thank you, Arvind.
Great, Ranjit. You really have a fantastic physicist look, actually. I think you're the only one who looks like a good scientist here, Ranjit, with that beautiful look. Okay. So neither me, Fatwa, and Himanchi look like a scientist, actually, like you look like. So yeah, thanks.
I don't know whether it's a compliment or...
Definitely a compliment, Ranjit. There is one who looks serious in the team. I think we need that look, actually. Yeah. So thank you. Thanks to both of you. So we have good vision. We have a good set of people. We have demonstrated good abilities. But just wanted to say to the people who thinks that India doesn't have facilities. I just want to show a very quick thing. We have one of the world's state-of-the-art facilities at our center. That includes a fantastic customized scanning electrochemical microscope and a very nice spectroplurometer with all the add-ons. And I'm just moving, like you just keep having fun as I move on. Like all like multi-crore instruments are there in our center, actually. And literally whatever you think of and whatever the machine that is required to do solar water splitting and associated photo and photoelectrocatalysis, we have them. In the next few months, we are also adding to really advanced machines, piezo force microscope, which is specific for photoferroic water splitting. And this is an advanced version of AFM. We are also adding an impedance analyzer. In fact, we have more than 3,000 square feet lab with all these facilities. Hopefully after COVID, we'll be able to come over and then we'll be able to spend some time with that. I look forward to interacting with all the brilliant minds who are attending the seminar today, and also industries who would be willing to work with us in solving the real world problem related to hydrogen. And here are the email addresses. If you want to have something like questions or thoughts for us, please do feel free to share. With that, I thank Himanshu and Ranjit as well as Fatwa for the session, and we go to the next round of the discussions. Thank you very much.
Thank you very much, Aravind, Ranjit, and Himanshu. So that was really impressive. Very nice overview of the center and also the capabilities. So indeed, you guys have very nice facilities there which I hope will be able to develop this whole field even further, right? Not only for India, I think everyone's will benefit from the advancement of the things that you are doing over there. The multi-physics is also, the multi-physics element of the center is also very, very impressive. So I think this is actually what's needed from tackling such a problem. So I understand that now we are moving to the question and answer. So I already see now that there are a few questions that are posted in the Q&A box. So I'll try to read some, but maybe before I go on to that, I take the liberty for me being a moderator for asking just one particular questions first in response probably to the slides, the last slides that you saw regarding contact, right? So this is a wonderful center, and I think you are also inviting people to come and collaborate either from the university to industry. From our experience here of making of opening a facilities, this interacting with users are often something that's could be easy, but could also be complicated. So what is now your plan in actually making this available to others? How are you going to tap the, how are you going to make sure that the greater community in India, as well as in the world, will be able to interact and collaborate with you, both academic and industry?
Okay, thanks, Pato. That's in fact one of the most important questions, the sharing the facilities. I have a two unique way of answering this. One is regular users, the other one is advanced users. For most of the regular users, already we are like kind of opened up to any people. For example, if someone writes an email to us saying that, can we go and use it? We said, go and use them. The only constraint we have is we don't let them use it directly. Rather, we use our experts to assist them in doing those experiments. But then what we want to do now is, this was more like very ad hoc setup, like only the people who writes email to us are the ones who are getting benefited. Rather, what we are going to do is, we'll have our own, India has come up with a process called iSTEM, where we register all our facilities. In fact, anyone can see those facilities and then just book a time and then talk to the concerned person to it and then come and use it. We plan to put all these instruments in iSTEM. And eventually anyone who can register can come over and use it. And essentially the thing is that they have to find the time when the operator or the person who is in charge of the mission is available. Then going on to the advanced users, thing is that any mission that we have, it cannot serve all the fundamental purpose. We may always have to keep modifying them or adding some additional add-ons to it. So what we would like to do is, we would like to interact with the people and try to see how we can modify the setup in such a way we can find out the specific problem statement we are working on. In fact, we don't want to keep that mission ad hoc just like that. Rather, we want to keep improving their capabilities to understand complex problems. For example, with simulation, they come out with this might be the intermediates. But then can we experimentally predict that intermediate? That's a real trouble for us. So we can in fact develop, like for the advanced users who can come and get trained or can become a part of our center, or we can collaborate where they can. So as a part of the Institute of Eminence, we have exchange programs for both people from abroad to come over to India and spend time. It's for faculty, students, or postdocs. And similarly, the same options are available for Indian students as well. So considering this, we would like to literally keep upgrading the missions with expertise available across the world, right, so as to tackle the largest problems.
Okay, thank you very much, Aravind. I think we now can proceed to answering. So I'll choose one at random, probably. One is, there's a questions regarding water electrocatalysis with seawater. So instead of using fresh water, which we like to do in the lab, is there any benefits or is there any limitations from using seawater, from doing seawater electrocatalysis?
Okay. So I think I'll put it in, again, the same two categories, the futuristic and then the immediate requirements. If you want to look into the immediate requirements, seawater photoelectrocatalysis is going to be difficult. Whereas we really have to keep that as a futuristic agenda. You have to start doing the fundamental research. The problem is, instead of water oxidation, we are oxidizing chloride to get into chlorine. And on top of it, seawater composition is very, very different across the world. They have all ions calcium, magnesium, this, that, everything. They eventually contaminate the surface. We cannot run all of them through an RO process to do it. However, the key lies here to develop catalysts which are robust and doesn't like become sensible to all these contaminants inside the seawater. At the same time, it can only does water oxidation. This is, I think, is the key. I mean, I would like to also, with your permission, to pass a question on to Ranjit and try to see how we can work in terms of simulation in trying to find out what can be a good catalyst for this purpose. Like, is there a possibility to do the simulations and come out with some sort of options? So experimentalists, instead of trying to roaming around all the area, we can try to narrow down our agenda to select set of materials. Ranjit, could you please help me answer this question?
Arvind, can you just repeat?
Yeah, so what I was asking is like the seawater splitting at the moment is the biggest issue, right? So we have like the chloride oxidation or the contaminants inside the sea, other ions apart from H plus. So we have Na plus, magnesium 2 plus, calcium 2 plus, whatever it is. They contaminate the catalyst. Is there a possibility to design a catalyst which is robust enough that they don't become sensible to all these contaminants inside the seawater, and also target only the water oxidation instead of chloride oxidation? Do you think that simulation can assist us doing this?
Well, I mean, simulation will not exactly tell the same story, but it will give insight how to tailor such catalyst, because it involves a selective process that certain quantum mechanical interactions you have to block, and you have to allow certain quantum mechanical interactions. So it can give you ideas how to tailor these materials or design these materials. But exact answer probably, I mean, it still needs experimental contribution. But we certainly, the simulations, we can provide the insight that whether, basically it's a part of the screening. It's a screening the multifunctional behavior. So blocking few functions and allowing one function. So that's a part of quantum many-body theory analysis. So insight can be provided certainly.
Okay, great. Thanks, Ranjit. So.
Okay, sounds good. Yeah, so definitely there's also, I think, for the questioner, I think there's also a very recent, as far as I know, very recent paper in Energy Environmental Science that actually did some kind of an techno-economic analysis that compares the direct seawater electrolysis with all the problems that Arafin just mentioned with water purifications and then typical electrolysis. And their analysis seems to suggest that since water purification cost is rather insignificant in the grander scale of that plant operation, it is more beneficial to actually purify it and then feed it to the current electrolysis system that we have. But I suggest you then to look into the particular paper. So now I think we can move to the next question. So I think we had Ranjit and just now. So I also would then therefore like to ask these questions for maybe both Ranjit and Himanshi. I think there's this questions in the Q&A, and also something that I'm interested in is that how do you plan to actually couple or combine the simulations results from the DFT to the larger scale? So as I understand now, the scale of the simulations is pretty different, right? Going from the atomic, microscopic, and then what Himanshi is doing is in a macroscopic scale. How is the interaction being expected? And one of particular questions that is out there in the Q&A is there any plan to that actually make an AI let me see, to this artificial intelligence that Himanshi was mentioning earlier, in also helping to do some materials prediction in your case, Ranjit?
Yeah, so okay, so it's a very nice, wonderful question. So let me tell the story. So if you examine the property at the atomic scale, it will give you the block phenomena, the phenomena at the bulk level. It's not the other way around. So if the property is absent at the atomistic level, then you will never see that property at the bulk level. So what we do is that we examine at the atomistic level, pass that information to people who are working on a macroscopic model. So macroscopic model have their own constraints, which are not related to quantum many-body theory that people should know. So those classical phenomena, I think the microscopic models can address. Yes, as far as the machine learning and artificial intelligence part is concerned, I think Himanshi has that expertise. We work in a very large configuration space. So we provide a good number of features which can serve as an attribute to the machine learning that in turn provide the suitable candidates for be it water splitting, be it CO2 reduction, be it anywhere else. Yes. Maybe Himanshi can add a bit into it.
So Ranjit gave a very nice explanation of how these two scales are connected to each other. Just as an example, at a macroscopic level, when we solve these conservation laws like conservation of mass, momentum, energy, we need certain properties there, as well as specifically to the chemical reactions that are happening. So Ranjit, through his DFT calculations, he can find out the activation energies and other properties which are needed in the chemical reaction networks. And these chemical reaction networks then can be used in our traditional macroscopic equations. So that's how we can link these two atomistic scales with the macroscopic scales. Now, the coming to the AI part. So first, my plan is to use this AI for the macroscopic level. So once we develop these first principle based models, even using the DFT based calculation based rate parameters and other properties which Ranjit will provide us, these models are going to be quite computationally expensive. We can't expect them to find out the entire parameter space to find the optimal design of the reactor or the system. So at that level, we want to use machine learning or artificial intelligence to develop some reduced order or surrogate models for our detailed system, and then use them to do a parameter search to find out the optimal design. So we'll start with that.
Okay, thank you very much for very clear answer, Ranjit and Himanshu. I think we can go to the next one. Yeah, so there are a few very specific questions regarding the materials, but I think some of you are trying to answer that anyway. So I'd like to maybe now move to another questions, which is you show a lot of research plan, right? And of course, the research center is very much directed towards this. But what about what other activities does the center plan to do in terms of dissemination to the public, as well as the teaching or education? Is there? I assume there would also be some kind of a plan in doing this.
Yeah, great, Fatwa. I think it is. I think the societal impact is something we really have to target to, apart from the technological impact. And we are very much committed to it. In fact, Government of India's all funding agencies now they have that societal impact business. What we are planning to do is hopefully to try to develop a very targeted course for industries where they can get educated about the solar cells independently, electrolyzers independently, and then try to see what are the problems that are existing so that they'll know exactly the state of the art, and then they can build on the top of it. So we are planning, like at the moment we are in discussion or talking about or discussing about it in order to develop such a specialized courses. On top of it, we are planning to introduce a handful of courses relevant to green hydrogen alone. And there is one course already running. We are independently running that course, which is called Solar Photoelectrochemistry, which is targeting on fundamental understanding of semiconductor electrolyte interface. And in order to reach a larger audience, hopefully there's some thought running in my mind. At later point of time, we need to have a specific MS program or MTech program, which is giving more insights and a lot of knowledge relevant to green hydrogen. It's not only the solar, it can be thermochemical, it can be anything, but completely relevant to the green hydrogen. And these are the multiple avenues. And apart from this, there is also, you talked about dissemination. One thing that people typically doesn't know is we always talk about there is a lot of solar energy available. If you ask how much is actually available, and that is a fundamental question that none of us really know. There is one number in some website, and if you try to make sense out of that, it gets terrible. So we are trying to really give that kind of information too, so that public knows what is the reality, and what are the solar energy available, how much of it can be converted to hydrogen. In fact, me and my students were discussing on writing a short blog on it. We keep updating that. This is what is the reality. This is what you have to do in order to get green hydrogen. So we don't just go by the newspaper articles where they say, yeah, these guys did a great thing. But then what that grade we need to quantify. Only then that will make sense. And so these are the multiple ways we are trying to address this issue. I think probably we can also grab like some of the students in that panel, like you can see some of them. If you want them to just say what they expect from a center like this,
Yep.
like, yeah.
That would
So
be great.
yeah. So whom should I grab? Or at your purview?
You're still muted, I think.
No, me?
Oh no,
Hi,
Hamdan,
sir.
is it?
Hi. Yeah, yeah.
Hi, yeah.
Hi, sir. So from a student's perspective, I think first and foremost, so these centers are like will give an exposure for industrial exposure. So I think centers like CPEC, so they act like a bridge between the industry and the academia. So industries, they will try to solve their problem, and as a student, we get a chance to know the end user requirement. So it is like a win-win situation for both the parties. And here we have a chance for a spin-off too. And another thing, it's we have this getting expertise in these state-of-the-art facilities for fundamental research. And as Arvind already mentioned, so this complementary expertise. So I work completely on experimental part, and if I need something on computation, so I think this center will have faculties who has an expertise in this thing. So I think that will be really helpful for my work. And I think definitely this center will be like very beneficial for the students. That's what
Thank you very much. I think that's certainly great to hear the perspective of the student, and I hope really that the center will be one of the things that you mentioned just now. I guess we can move now to there's a few questions in the Q&A regarding efficiency. Is there any particular target? So how much is solar to hydrogen efficiency that we need to actually get in order for the commercializations to happen? I'm guessing that this is also depending on the type of the division that you made in whether it's the industry centric one and the futuristic idea that you put in for the direct water splitting.
Yeah. So Fatwa, I think I mean, like, the efficiency is one parameter, but after talking to a bunch of stakeholders in the industry, I've understood that they care about cost of hydrogen per kilogram. I think that seemed to be the final and ultimate number that anyone, any commercializing, any venture capitalists, investors, anyone is interested in. So in terms of efficiency, I mean, as a person coming from the academic institute, now I will take simply like kind of commercial solar panels are at nearly 16% efficiency. Like on average, you will get 16%. That's like kind of, if you go to the real big ones, you get 20. So imagine electrolyzers operate at 70 to 80% efficiency. Like they're really good at it. So if you just multiply that, you're already at like 10 to 12% efficiency, considering all the losses through the electronics, everything. Even in the worst case scenario, we may get somewhere around 8 to 10% efficiency from the sunlight to the hydrogen production. So the end to end efficiency. When it comes to that, I think that is a kind of very meaningful number. And I've seen DOE predictions, like cost of hydrogen per kilogram was like kind of like $6 at the moment. Like that's not like kind of including all the associated like electronics and everything. It is just from the electrolyzer connecting with solar cells. Of course, if you include the cost of transportation, cost of storage, the cost will eventually go up. So they're putting the number somewhere at around $6 per kilowatt, so per kilogram of hydrogen. Okay. However, the present hydrogen is around like less than $2. So we have a bridge, like gap of nearly $4 out there. So rather than talking about efficiency, I keep that number, how I can bring that number down. And one of the ways is improve the existing system efficiency, like efficiency of the existing photoelectrochemical system. For example, if you move from solar plus electrolyzer to completely photoelectrochemical system, the advantage is we are moving from two system to one system business. And in the one system business, if we can get like that same 10% efficiency, then I think we are at the cost advantage, like on the dollars per kilogram of hydrogen. The other issue is that when you go to the PEC, the photoelectrochemical like single system, it has its own plumbing lines, hydrogen collection issues are there. So I think The moment when you go to the large implementation, we will get to know the actual issue. Ideally, simply I'll put it this way. If you follow the trajectory of solar cells, they've started at 6%. When they got into 23, 24% like silicon, people started thinking about the actual commercial reality. I think at the moment, our target is to really probably blindly follow the trajectory. Is there a way to really go to 15%, 20% efficiency? But that's a very, very like a very difficult target to achieve. But I think we need to identify how to reach that number in order to put that green hydrogen in the commercial perspective.
Yeah, yeah. So the center doesn't have. Is there any particular clear milestones in 5 years or in 10 years that the center would like to achieve, maybe in terms of either efficiency just now or the scale, for example, with the combined with what Himanchi is doing with the simulation, of course. Is there any particular number, milestones?
Yeah, we do have a milestone. When we established a center, we also got one thing very clear, Fatwa. That is, we wanted to really develop a new field of science also. I think one thing we had in mind is when we saw Lawrence Berkeley National Lab or Helmholtz Zentrum Berlin, or any of these national labs for that matter, they are like really good at something. And I think they're known for it. Whenever we think of a topic, we automatically mind goes to that specific labs. Honestly, whenever people talk about bismuth vanadate, I just remember Helmholtz Zentrum Berlin, because you guys are really good at it.
You are too kind. You are too kind.
Truth. So, the thing is, me and Ranjit had a kind of lot of discussion. We said, we will develop this photoferroic electrochemistry. How the distortion, let it be a local distortion, which is like globally, there will be no polarization. The distortion leads to polarization. And globally, there will be no polarization, which is the centrosymmetric materials. On the other side, we have ferroelectric systems, which are like permanently polarized. And what we want to do is, one of the biggest milestones, or what we want to be known for, is what is the role of distortion and eventually the polarization, and finally their role in the water splitting. In this case, we are not really concerned about efficiency, although we anticipate the performance also to go up. It may go either way, but we wanted to be really known for that specific field of science. That is on the fundamentals perspective. When you go to the applications perspective, in 2 years down the line, we would like to really have a large area, 100 centimeter square, a photoelectrochemical cell delivered from, already we have demonstrated in the Angavante paper, we have shown CS2PTI6 to be one of the best ones. We are working on really to make like 100 centimeter square cell, like as a demonstration, which survives with at high currents, 3 to 5 milliamps current, and then survives for at least 1,000 hours under simulated sunlight condition. On top of it, we have the other industry agenda, which is kind of very ad hoc, and it will be floating agenda depending on what industries look for. But we wanted to do one big thing by the end of 2 years. The big thing is, the efficiency of electrolyzers are very much dependent on the solar power coming in. We wanted to, with our systems integration person, we wanted to develop an algorithm which can track the outcome of the solar panels and eventually try to optimize the efficiency of the electrolyzer, because in the evening we cannot operate all the electrolyzers, because the electrolyzers operate at very low efficiency when we go to low currents, and eventually the collection efficiency of hydrogen will also go down. So one of the other things we are planning is that we need to really keep that target very clean. We really assist industries to say that we will try to build an algorithm in such a way that it will track the solar power output and accordingly distribute the power to the electrolyzers in order to maximize the outcome of like output efficiency. Those are the three agenda that we have for in terms of long-term as well as the short-term perspective.
Right, great. Thank you very much. The next question from Gugulat Fankana is wondering whether the DFT calculation is capable of actually looking into the effect of irradiation with solar spectrum. So most of these things were probably, this is probably for Ranjit. Then how do we look into this?
We DFT calculation cannot take solar irradiation, but effect of irradiation on the materials can be examined through DFT.
Yeah, good, short and sweet answers. We can do that. Thank you very much. Yeah, so the next question is probably related. I'd like to addressed it to Himanchi. I'm also in our institute. We're also working a lot on a simulation and for scaling up photoelectrodes. I'm just curious on the scale for which you think you could actually see as effective, or what at what range should you actually focus on, as well as whether you are also building validation experiment expertise as well in addition to the simulation, because there is one thing, but then the prototyping and the demonstration is, if in my opinion, is also as useful to actually validate the model that you're developing. Maybe you could comment on that.
Sure, Fatwa. So we take this approach of multi-scale simulations. So in terms, you raise a very important point. How do we validate these complex systems? So for the validation purpose, the plan is that we'll start with something small, basically the models at the small scale. So whatever chemistry Ranjit is going to develop, the first target will be validating that chemistry itself before combining it with any transport process. Otherwise, what happens when you have these multi-physics, multi-scale simulations, I have seen in literature a lot of problem is that since a lot of complex things are happening and we don't know many of these parameters, there's a lot of tuning and optimizing the model is going on. And that, I believe, is not a robust validation, because in that case, we are basically developing a model for a particular system at hand rather than a general model which will be able to predict something which we are not studying at present, in the present moment. So the aim is to make these things, these different physics, independent of each other while validating the models. So as I mentioned, validating chemistry itself without any transport effect is an important first step. And then combining it with something, a simple transport phenomena like heat transfer, and then testing it in the, comparing it with the experimental results. So having this controlled experiment with a specific task that we need to validate our simulations and models is very important. Otherwise, if experimentalists are developing their lab scale experiments separately and simulation people are doing it separately, then it becomes very hard to bring them together. So that's why during the starting phase of the proposal itself, me and Arvind and Ranjit, we had a lot of discussions. And this thing was clear that we'll have to develop experiments specifically for simulations, and we will be doing simulations keeping the experimental aspects in mind so that they go hand in hand.
Very nice. Thank you very much, Himanchi. So we, as far as I understand, the discussions can actually continue on. Unfortunately, I have another appointment in 5 minutes, but so that's why allow me to then ask a final questions that is also somewhat related to one of the questions that is typed in the Q&A regarding the Indian scenario regarding hydrogen energy, and how do you think, what's the, probably if we want to rephrase it a little bit, right, and maybe add one more point that I would like to ask you is that what's now the challenge in implementing hydrogen in, you think, in India, and how do you think the center will help that? And I actually also heard from your talk earlier that India is not planning to reduce its coal use. So do you see a possibility in the future, or is it already in fact planned to increase the scope, to widen the scope, to also include CO2 reduction, right? Because then you can tap into the output of this coal power plant and do CO2 reduction on site, and do that, or basically, or are you planning to basically focus on hydrogen for the time being? Go ahead.
Yeah, thanks, Fatwa. I think I can quickly answer this specific thing. So in India, I think, honestly, I talked to a handful of stakeholders, including policymakers, like some of the top level company personnel in the past 3 to 4 weeks. And there's like no clue on how to really proceed further. I think essentially they're waiting for government to give a kind of strategy roadmap that they can implement and then eventually put them to real thing. So, but one thing they're very sure of is they want to combine the solar cell with electrolyzers. That is something they're very sure of. I think, as I've said at the beginning, this technology is going to take the front line at least for next 5 to 7 years, and until we show the peak to be coming out. So in Indian scenario, almost all the stakeholders are looking for now one of the key things, how to improve the performance of electrolyzers. That is one thing that they're really looking for. And they also do not know how to characterize and study the accelerated testing for electrolyzers, because we have the testing for batteries, we have it for solar cells, but we don't have that for electrolyzers. And I think they are really concerned about it. Like, can I have some data that can help me really take it forward? And I think that is a big gap. That's really like kind of a hurdle for the Indian industries to step onto this technology. And the other thing that I've also found is that they also want to make sure that, as I talked before, the algorithm that I mentioned, how to keep the electrolyzer as well as the solar cell at maximum performance all the time. And that's something, that optimization process is something that they're really looking into. So I think if you try to address all these things, India would be quite happy for next 5 to 7 years. I'm very sure about it. It's more about beyond that, we have to keep pushing the pushing like scientific outcomes much better in order to move from two system solar plus solar panels for electrolyzers to pure photoelectrochemical systems. I think, yeah, that's the gap I believe that we should probably, and of course you talked about CO2. We have also a separate center on carbon dioxide, CCUS. We have a separate center granted by Institute of Eminence. And fortunately, I think me and Himanchi are also part of that team. It's called, we are like more like a
nice
contributions there. And they're really targeting that CO2 thing. You know, the solar panels and electrolyzers are already advanced technologies, whereas CO2 sequestration is like slightly advanced, but then utilization part is still like at its nascent stage.
Yep.
And that center is specifically targeting at that only issue. Like the way we are targeting only hydrogen, they are targeting only CO2. They like CO2, we hate CO2. And yeah.
I see. Oh, great. Yeah, then with that, I think, yeah, so as I understand, the discussion can continue, but I would probably use this opportunity to thank again Arafin, Himanshu, and Ranjit, and also all the other organizers of this webinar from IIT Madras, and for the nice discussion. Really thankful for that, and I'm really excited to see the center. And I hope at some point post COVID we could really interact in a more personal level, right? And I really look forward to see wonderful results from your center. I wish you guys all the best, and I turn it back to Arafin. Have a nice evening for you guys.
Yeah, great. Thank you very much, Fatwa. First of all, I think we should really thank you for spending time today to do a fantastic moderation. It was really a nice thing. In fact, yeah, I take this opportunity to thank also Matt, who connected me with you. It's great interacting with you the past few weeks. And so essentially the moderation was excellent, and a lot of suggestions from your side is excellent. We also look forward to interacting with you, learning from the way you run the center, so that we can also implement some goodwills from there to here and eventually reach a good outcome. Yeah, we look forward to interacting with you sometime soon, Patwa. Thank you very much.
Yeah,
and we can continue the discussion soon. Thanks a lot.
Bye. Have a nice evening. Bye from my side.
Bye. Yeah, good afternoon. Thanks. Bye. So now I think we can probably take another 10 minutes to finish the whole other questions off. Is that all right? Like, I just would like to see the conference organizers out there.
Yeah, you can go ahead.
Can we take another 10 minutes? Will that be all right to answer the questions out there?
Yeah, Dr. Arun, you can go ahead.
Great. Okay. So I think probably we just can distribute a bit of the questions to like Himanshu and also Ranjit. The first question is essentially answered. That's the last one. I think we can move this out. And there is a question from Akhil. What are the other photo and electrochemical applications or challenges are being solved by CPEC other than solar water splitting? What is the scope of CPEC? Okay, I think I take privilege in answering this question, and I also grab Ranjit and Himanshu over. So CPEC is not, although the center's name is very generic, Center for Photo and Electrochemical Energy Sciences. But then the thing is that we are targeting only hydrogen at the moment. Of course, if there is a necessity to move on to other technologies, like we want to convert nitrogen to ammonia using solar energy or using electrochemical energy, and if there is a significant necessity, we will move on to it. And we will probably even do a part of our work on those like long-term visionary ideas. However, majority of our interest will still remain with the hydrogen, because that is our immediate requirement. We really need to address that for the nation. Whereas there are also other projects like batteries. We work on nitrogen reduction, and in fact, we will also probably contribute to some extent in interfacing with our carbon dioxide research, where we convert carbon dioxide to products. Himanchi or Ranjit, could you also just like try to see what are the other things that we can potentially do based on experience, like biofuels, for example? Himanshi, is he around? Himanshi is not around. So it looks like, yeah, probably, yeah, okay, great. So I'll go to the next question then. Can we feed ad data, and any AI can be used for this? That's from Sangeeta. Yeah, that's exactly, yeah, it's possible. At the moment, we don't know, like we are not really focusing on this area. We'll have to see how to, the AI at the moment is being very much used for the materials development alone. But yeah, at least that's what we understand and we know. But that's a good idea. We may have to think about it in future. And the peroxide are better than single atom catalyst, and how? I couldn't really understand that question. I assume that the person is asking about single atom catalyst. Single atom catalysts are nice, but then at the moment they aggregate quite a lot, and that kills the performance in the long run. So hopefully, if we solve that, probably we'll be able to use the single atom catalyst. They are really beautiful in terms of performance, but the thing is that stability wise, they still take a backseat. Hopefully, we'll be able to solve that. And yes, that path regarding is there path regarding simulation? Ranjit, do you want to just add that one? Is there trajectory? Oh, Ranjit.
What is that question?
So question is like what they've asked is there path regarding simulation? So what I've understood is maybe they're asking, can simulation assist in any of the agenda that we have for hydrogen production in terms of materials or in terms of device level? I think that's their question, I guess.
So not at the device level, but at the tailoring of materials level, the simulation will give. See, I think first you have to develop the mechanism. So once you develop the mechanism, then you can tailor the materials at the large scale. So the simulations, like atomistic level simulation that I do, is not at the device level. It's giving the mechanism and suggests that this or that material is going to be helpful or beneficial for any particular functionalities, be it water splitting or CO2 reduction or designing a battery material. But then I think those who are doing macroscopic simulations or modeling, I think Himanchi is a part of that. So they can help in bringing to the device level characteristics.
Okay, okay. Ranjit, just as a side note, what is a single atom catalyst? I mean, that's one of the biggest domains of research in the catalysis, right? Single atom catalyst for, like, let's say for water oxidation or water reduction, whatever it is.
I think in single atom catalyst, what they are trying to look at this. See, if you solve the Hamiltonian for a single atom, it has its own discrete energy level. So how the excited states being used through this irradiation or anything, any external energy, and how they are going to contribute towards the catalytic phenomenon. That's what they are talking about in general, single atom catalyst.
Okay.
Single atom catalyst is still at the conceptual level. I don't know whether we have come to the realistic level of implementing that in the real scenario, but it's still at the proof of the concept level.
Okay. Great. I mean, nice to hear your perspective on a single atom catalyst. Although we interacted quite a lot, we never talked about this specific aspect of catalysis. Yeah. Great. Thank you, Ranjit. I'll move on. I think literally we are done except on last question. After PhD, is there any possibility to do any course or any short-term course or any knowledge gaining possibilities while working as a faculty in self-financing institutes? Yeah, so I think that is a question from Mr. V.S. Kumar. Definitely, sir. I mean, so at the beginning of this, the whole discussion, or even before the start of this talk, there was a video played from our institute, OG office, Global Engagement Office. They showed that we have a good NPTEL, like our Swayam Prabha, where you can take courses. There are too many courses related to energy, related to renewables, related to specifically to batteries, specifically to electrochemistry, specifically to DFT. There are so many courses, like several thousands of courses are there. Definitely, you can take any of those courses and then try to try to enhance your knowledge in the subject. That's I think a best opportunity to learn, I guess. NPTEL is like beautifully well defined, and I think the standard of the courses is very similar to the courses we typically take for our own students at IIT Madras on campus. So I think in terms of quality, we are not compromising at NPTEL. They are really beautiful, and I strongly recommend you to look into that NPTEL course opportunity. I think looks like Ranjit and also team, looks like we have nearly answered all the questions. Are there any other questions that I want to ask? If not, we can wrap the session up. Okay, looks like there are no further questions. So I think I would like to take this opportunity to really thank all the participants. And it's really a pleasure to like talking about the visions of our center and what we have achieved so far. And so that's that's very phenomenal. Sometimes talking to people outside because of this COVID situation has gone limited. And like the panel discussion we have had literally tried to evade that small portion of COVID era online meetings. It was really like almost like one-to-one discussion. And we really look forward to solving one of the world's and India's greatest challenges, that is moving to the green hydrogen. And I thank again all the panelists and our students who are present here, and also our organizers. They really did a phenomenal job, fantastic job out there in organizing the whole thing. And also, I think I should thank Fatwa, although he is not here. He like from Helmholtz Center Berlin, Germany. He took 1 hour of his time to spend with us discussing his thoughts and also discussing our ambitions. With that, I'd like to thank you all very much. We can formally close the session. Thank you. Have a good time. Stay very safe.
Yeah, thank you, Dr. Aravind. Thank you, Dr. Nanda, and thanks everyone. And we have our next webinar on September 2. So we request the participant to register for that. And thanks everyone.
Thank you very much. Thank you. Thanks a lot.
Yeah.
Take care. Bye-bye.